All right, so they tell me part 2 of the fundamental theorem of calculus says that if a function is continuous on the interval from a to b, then the integration of f of x from a to b will be capital F of b minus capital F of a. So basically the antiderivative with b and a plugged in. So we know that formula. We've seen that before. Where f is that antiderivative. So that means that if you took the derivative of capital F, if you took the derivative of the antiderivative, you would go back to the original equation. So that equation could also be written as, if you integrate the derivative and they cancel each other out, you'll go back to your original function, but you'll plug b and a into that. And so that would show you the total change over your interval that you're working with. So on the bottom of 349 it continues, we know that capital F derivative of x represents the rate of change of y equals capital F of x with respect to x, and f of b minus f of a is the change in y when x changes from a to b. So we could reformulate the second part of the fundamental theorem of calculus in words as follows. And that is the total change theorem on the top of 350. And here's what the total change theorem says. The integral of a rate of change is the total change from a to b of the derivative of that function, and that would give us f of b minus f of a. So they go through and they give me, there on page 350, a ton of applications of this so that we can understand it better. Some of these are ones that we've seen already this year. They talk about chemical reactions and they talk about linear density. Let's skip down to the fourth one there on page 350. They just have little dots out beside them, so count down to the fourth dot. It says if the rate of growth of a population is the rate of change of n over the rate of change of t, then the integration of that function dn dt from time 1 to time 2 would equal to n of t2 minus n of t1. Here's what they're saying. If you integrate the derivative, you integrate the rate of change. Remember, derivative is a rate of change. So you're talking about the rate of change of a population over, let's say, 10 years. You're looking at the rate of change of the population of Savannah from 2005 to 2015, okay? So if you're talking about the derivative as a rate of change, if you integrate that derivative, you integrate that rate of change, they cancel each other out and they take you back to the original function. They took us back then to the original population equation, and we could plug in 2015 and 2005 and literally see the total change in the population between those years. Look at the next one. If C of x is the cost of producing x units of a commodity, then the marginal cost, of course, is the derivative of that. So if you integrate the marginal cost, you integrate the rate of change, the integral and the derivative cancel each other out and take me back to the original cost function. So then I would be plugging in x sub 2 and x sub 1. That would show me the total cost of producing that many items. So maybe I was looking at, x sub 1 was 0 and x sub 2 was 1,000. That would show me the total cost of producing 1,000 items. Look at the next one. If an object moves along a straight line with position function s of t, then its velocity is the derivative of s of t. So if you integrate the velocity, that's integrating the derivative of s of t. They're going to cancel each other out and just take you back to that original position function where you would plug in time 2 and time 1 and you would be able to see, hey, here is the change in my position from this time to this time, okay? So that's the idea of the total change theorem. It can show me the total change in position, the total change in cost, the total change in population, and we have tons of different examples there. I don't often tell you that you need to read this whole section. It's always a great idea, but this is one of those things that you really need to read pages 349 to 352 for you to really grasp this concept and for it to sink in. We've taught through a couple of these examples, but it would really help you to go through some more. So continuing on with that idea that we were talking about with a position function, They tell me that when I do that integration and I get s of t sub 2 minus s of t sub 1, that is its change in position or its displacement. So the displacement of the particle during the time period from time 1 to time 2. So we're going to be able to find the displacement of something just by doing that normal integration like we were just talking about. However, distance is not the same. Let's say that you're parked in parking spot 100 in the parking lot. You drive down to Ronnie's and get a world famous milkshake, and you come back and you park right back in parking spot 100. What is your displacement? 0, right. But is your distance 0? No, there's going to be some miles on your odometer, right? So displacement and distance are not the same thing. I may, if you're thinking about like north is positive and south is negative, or east is positive and west is negative, you may go a positive 2 miles down the interstate and come back a negative 2 miles so that your displacement is 0, but your distance would be 2 plus 2, it would be 4. And the way that we would address that is by doing the absolute value for distance, right? And so that's exactly what they tell me, is that for distance, I'm going to need to do the absolute value. So let's say that I'm looking at this particular figure over here. For displacement, I'm going to go through and have a positive value, a negative value because it's below the x-axis, and then another positive value. So depending on which of those is larger, the positive region or the negative region, I would get a positive or negative answer. However, when I want to look at the distance, I'm going to use this value. I'm going to have to make this value positive because the absolute value of a positive is a positive, but the absolute value of a negative is a positive. So I'm going to have this positive value, this negative would change to a positive, and then this positive value. So that when I go through, all of those values are going to be positive. So that's how we could like symbolically look at it in terms of a graph. All right, so let's look at example number 6. All right, example 6 says a particle moves along a line so that its velocity at time t is represented by the equation v of t equals t squared minus t minus 6, measured in meters per second. Find the displacement of the particle during the time period 1 to 4 and the distance traveled during that same time period. Okay, so we start with displacement, and we said that displacement was just going to be the normal integration. So let's go through and do the definite integration for this guy. They told me to go from 1 to 4, so starting at t equals 1 and stopping at t equals 4. All right, so what's the integration of t squared?
1/3 t cubed.
1/3 t cubed. Integration of negative t?
1/2 t cubed.
Negative 1/2 t squared, right? And then negative 6. Negative 6t, right. And here's that same notation that we've been using once you do your antiderivative, that you can say, okay, I haven't plugged in the 1 and the 4 yet. And remember to put parentheses around that entire thing. If you don't, then it looks like you're only plugging 1 to 4 into this last piece down here. So I want to be sure that I put it in the whole thing. All right, then we just have some joyful computation to do. We can go through and plug in 4. So 4 cubed is 64, times 1/3 would be 64 thirds. And then 4 squared is 16, so half of that would be 8. And then 6 times 4 is 24. Same idea, plug in 1. And then we just have some fraction work to do. So we could go through and say negative 8 and negative 24 is negative 32. And I'm going to write this improper fraction as a mixed number. And then over here, positive 1/3 minus 1/2. If I got a common denominator for that, we're looking at like 2/6 minus 3/6. So negative 6 and 1/6. Minus a negative would be plus. And thankfully, we already have a common denominator here. So we can say 21 and 6 is 27. And then 2/6 and 1/6 is 3/6, so 1/2. Minus our 32 is going to give us a negative 4 and 1/2. So when I see a negative with an integral, remember the only way that that can happen is if a portion of my graph was below the x-axis and the larger portion was below the x-axis, or all of it was. I can have a portion above and below, but if my answer is going to be negative, the larger portion better be below the x-axis. Or it could be something we've seen before, like maybe it's a discontinuous function that I just overlooked in the very beginning. So if I go back and I look at the graph, here's t squared minus t minus 6, what we were working with. Here's the graph of that. And if I'm looking at it from positive 1 to positive 4, sure enough, I do have a larger portion below than I do above, so it makes sense why I'm getting a negative piece that's larger and why my final answer would be negative. You know, as smart as that graphing calculator thing is, you would think that there would be a way to do these on the calculator. Well, grab your calculator because we're there.
Calculator.
All right, so there are several different ways that you can do this on your graphing calculator. You can do it on your main screen. You can do it on your graphing screen. We're going to do it each of those ways. So let's start with the main screen, assuming that mine decides to cooperate.
Think about using this. Okay.
Here's how you can do this on your main screen. All right, I'm going to go to math. The same place that we found n derivative, you also have a function integrate. So I'm going to go down to number 9, function integrate. If you have the new operating system, this is the beautiful thing that it's going to look like. If you happen to have an 83 or you don't have the new operating system, then you're going to need to type it in like I've got it here on the board. You're going to type in function integrate and then the equation comma t, comma a, comma b, and I'll have that in the notes in just a second. But you can see if you have not for some reason downloaded that new operating system, you can see the advantage of it right here, makes it worthwhile. So I'm going to go through and our a value was 1, our b value was 4. Our equation was t squared minus t minus 6. I'm going to use x. It's just a variable, so it doesn't matter. X squared minus x minus 6. And then I need to tell it what variable to use over here, so I'll tell it x. And that's the exact same answer that we got a second ago, right? Now, there's also a shortcut for getting to this screen. Instead of doing math and derivative, you also, if you have the new operating system, you can do F2. And there it is, number 4 right there is function integrate. So if I choose number 4, it puts that notation up there as well. That's another way to get to that same notation. Okay? Now, you can do it that way, or you also can go to y equals and type in your equation. So we've got x squared minus x minus 6. Just 6, not 2 of them. All right, then I'm going to go over to graph, and I'm on a zoom 6. You can be on whatever zoom you want. So we can see we've got a pretty good image there. I'm going to do second trace, which is my calculate menu, and I'm going to choose number 7 down there. See function integrate right there? So I'm going to choose number 7, and when I do, it says, what's your lower limit? Now you can toggle to it if you want to, like you can, use your arrow keys, but it's a whole lot easier, particularly if you've got to put in something like 1.723. You just start typing and it'll take it. So like we were doing from 1 to 4, so as soon as I type 1, you'll notice that it accepts that. I don't have to scroll to it. So I'm going to hit 1, enter, and then same thing for upper limit. You can scroll to it or you can just type it in. So I'm going to type 4, enter. Now look at that happiness. It's about the same amount of work to put it on the main screen as it is to put it on the graph, and I just like it on the graph so much better. Here's why. If there's a discontinuity, I'm more likely to spot it here, right, and not overlook a common mistake like that. Plus, if I'm getting a negative answer like we are for this one, it's easy for me to see that that's legitimate, that the larger portion is below the axis and the smaller portion is above. Okay, so that's the same problem that we just did where we got the negative 4.5, but we saw on the calculator a couple of different ways that we could do that. Here it was on the main screen, and here's that classic print if you have an 83 or have not gotten the new operating system for the 84, and then here is that math print that we had. Additionally, here was the alternate way that we did it, where we went through and we put in our equation, graphed it, and went through the calculate menu, gave it the lower and the upper limits, and it gave us the drawing and the area both. All right, so now that we've got the displacement, let's calculate the distance. Now, remember we said for distance, you're going to have to do the absolute value, and we've already gotten a good idea that part of this is below and part is above, that we're definitely going to need absolute value for this. So I'm going to go through and redefine my absolute value as a piecewise defined function. So if I make a sign graph, we've already solved this and gotten the x-intercepts of 3 and negative 2. So here's negative 2, positive 3. I can pick a test point like 0 and plug it in, and I'll get negative 6. So if it's negative here, cross a single critical number, the sign changes. Cross a single critical number, the sign changes. There's my sign graph. So from negative infinity to negative 2, it's positive, so I would get the exact function that I started with. From negative 2 to positive 3, it's negative, so I'm going to get the opposite of the function that I started with. And then from positive 3 to infinity, it's positive, so I'm going to get the exact function that I started with. We are only interested in the piece from 1 to 4. So if I start at 1, then that's going to be this middle piece right here. From 1 to 3, I'm going to use the opposite, and then from 3 to 4, I'm going to use the exact. So again, from 1 to 3, I'm going to use the opposite of my function, and then from 3 to 4, I'm going to use my exact function. Now, when we did the integration on this a moment ago for the displacement, the antiderivative is going to be the same. It's just that, of course, each of the signs is going to change, right? And the antiderivative is going to be exactly the same for this one because the signs didn't change at all. Now, I don't have any doubt that you can plug in a bazillion happy little numbers into your calculator. You do not need to write down all of this tediousness down here. You can just say that it's equal to 61 over 6, but I always like to work it out for you so that you can see how we can come to that precise value even if we don't have our calculator. But I know that you are pros at fractions and combining values. Now, at the beginning of the year, we talked about lies my calculator told me. Here's a little white lie that your calculator will tell you. It's not a really big major thing, but your calculator will not do absolute value integrals completely accurately. It just runs out of space and it rounds them off, and so it'll end up being off, not by much, but maybe just by like a couple hundredths or a couple of thousandths. So if you're on the multiple choice portion of the AP exam where you have a graphing calculator, if you had an answer that was very close, it was only off by a hair, then you would just know that was the right thing. But if you were on the FRQs where you had to give the exact value accurate to 3 decimal places, do not rely on your calculator to do that. Here's a way that you can get around that. You're going to start this problem by setting it up as a piecewise defined. So we've got our, excuse me, thank you. If we typed in this absolute value right here into my calculator, it would not give me, sometimes it will, but it will not always give me as precise of an answer as I need. So what I could do is redefine it in the piecewise, and then I could throw this piece into my calculator and it will give me the 22/3. I could throw this piece into my calculator and it would give me the 17/6, and then I could add those and get that exact value. So that's a way that you can get around that little glitch on your calculator so that you know that you're getting the exact value that you need. So sometimes it will give you the value accurate to 3 decimal places. Sometimes it'll be off a little bit. Again, if you'll put this in and get this exact value, put this in and get this exact value, and then combine them, you'll be fine, as long as you don't put the original in and ask it to do that for you.